This is our second session of the summit. Uh, Joel will be taking this session. He's CEO and co-founder of Three Box Lab. So, and it will be a workshop. He will be showing the demo. So let's see. Welcome, Joel.
Thanks, Nikhil. All right, so I'll just jump straight into kind of the initial presentation.
Yeah, sure. The stage is yours. I'll be here on the stage if you need anything.
All right, so I hope you can see my screen. My name is Joel, and as Nikhil mentioned, I'm a co-founder of Three Box Labs, and we have been creating something called Ceramic. And today I'm going to be talking about how you can kind of use sovereign data to build Web3 applications and actually build Web3 applications that can really scale. All right, so let's start off by just talking about like what's actually sovereign data and why does it kind of matter. So sovereign data is really data that users have control over and actually have like some kind of cryptographic control over. And so instead of data kind of being locked into these data silos like Google and Facebook, you can actually give the users direct cryptographic sovereignty over their data. So in order to do this, we need some kind of verifiable data objects. So there's a few examples of this already. You have a file on IPFS that has like a minimal kind of cryptographic verifiability because you have a hash and you retrieve the file and then you can verify that the hash kind of corresponds to the file. Contract on Ethereum you can think of as like a data object that can change over time. And so that's controlled by like processing the state of the entire Ethereum blockchain. You can get the state of this contract. A JWT is just like a signed data object. So it's a JSON object that has some kind of signature. So you can verify that that object was actually authored by some specific cryptographic identity. But if we really want to have kind of sovereign data, we need something that's kind of much better than this. And so you need some kind of data objects that can change over time. And these data objects need a persistent identifier that doesn't change. So you can always kind of retrieve the latest state of this data object. And we need some kind of cryptographic access control. We can't just have like anyone being able to update this object because then essentially someone could spam this object and make it kind of like infeasible to sync it or whatever. And so you need some kind of access control that governs how this data object is updated so that certain entities can update it, but not everyone. And it needs to be scalable. And this means that like basically I want to be able to independently verify these data objects without having to sync this entire state of all the data objects. So imagine you're going to a website and you just want to get the latest comment on some video or something. You don't want to be able to sync all the comments on all the videos or even like all the websites on the entire internet to be able to like verify the state of those comments is actually the correct state that you're actually going for. So in the case of like an Ethereum contract, you actually need to sync the entire state of the Ethereum blockchain to know the state of a contract because these contracts have kind of interdependencies. They send messages between each other. But if you're only caring about mutable data objects, you don't necessarily need to have this kind of synchronicity between these data objects. And so we can actually make this much more scalable. I can verify state of like one comment section without having to verify anything else in the network. And so yeah, this kind of allows us to make the entire internet verifiable. And I talked about like this independent verifiability, but also it enables something which is called kind of no link rot. And what that means is basically right now on the internet, when you go to a website, you type in like a domain name and you basically tell your browser to go to some server and get some data. But if you put the link to some data in your website, the server might go offline or might be censored or something else bad might happen. And so now that your link is kind of rotten, it's like no longer valid. But if you use these kind of persistent identifiers to point to data, you could be able to link to some piece of data kind of logically, and then anyone that cares about it can back up that data and back up the data and provide it to the network. And so this kind of like makes the internet kind of way more anti-fragile. All right, so Ceramic is a protocol that actually enables this type of sovereign data, and it's done through something called stateful event streams. And so stream is essentially an event log, a log of events, and then there's processing done on those events, and then we derive a state, so the current state of this mutable data object. And so this kind of becomes a minimal building block for dynamic or like sovereign data. And each stream has a stream ID, which is persistent and never changes. But if you have a stream ID, you can always kind of get the latest state of this data object. So this kind of creates a global environment where data is shared globally. And if I have this stream ID of some data object, I can sync that from the network, and I don't really care about who sends that to me. As long as I get it from the network, I can verify that the state is correct. And now I have this guarantee that like the data I'm viewing is actually correct. And the commits, the events in this event log, they kind of originate locally. So if I have a stream that's controlled by my identity, I can author an event and then publish that to the network. And this means that I can actually like do optimistic application of the events locally before they're kind of propagating to the network. So if I make a comment, I will see it first on my machine, then propagate to the rest of the network. And yeah, so you can kind of use this streams to model different types of data. And this is what we use stream types for. So stream types allow you to have like a specific state transition logic and specific conflict resolution for this event log. And so if we dive a little bit deeper into how this works, a stream is essentially this event log of, we call them commits. And so each commit is signed. And you can see here in this example to the right, we have a Genesis commit. That's kind of the first commit in the event log that creates the stream. And the stream ID is based on this Genesis commit. And here we see after that comes an anchor commit, and this is essentially a commit that proves that the hash of the previous event has been kind of committed into a blockchain. And that's useful because now we can see like at what point in time that event happened. And so then we see a signature commit that usually contains some kind of patch or updates that describes, like an event that describes to the stream processor or stream type how to change the state of the event log. And then here we see another signature commit and another anchor commit, again proves the time at which this happened, and so on and so forth. So you can see that this event stream can keep kind of mutating the state of this object. And so when a Ceramic node comes onto the network and says like, hey, I want to load the latest state of this stream, the stream ID, it basically asks the network, hey, what's the latest update for this stream? And other nodes that kind of store this stream will be able to respond with a hash of the latest state. And then the node that made the request can sync the event log and kind of verify all of the commits of the state object and make sure that, okay, the state I arrived at is actually correct because all the signatures are correct, and we can, if there's conflicts, we can apply conflict resolution logic based on this time that we get from the anchors. Yeah, each of these streams are kind of processed completely independently. And we kind of get, and even if someone tries to respond with some kind of incorrect data, we'll easily be able to detect it. And so the stream processors are the things that kind of govern how state transitions happen in in the stream. So we can have different stream types that describes different types of data objects in the network. And the access control in these streams is controlled by decentralized identifiers, DIDs. So DIDs is a W3C standard for describing a system where it goes from an identifier, and from the identifier you can resolve a DID document. And the DID document essentially contains a list of public keys. That can be a public key for signature verification. It could be a public key for encryption. So if I have a DID, I can resolve the DID document and send an encrypted messages to that identity. And it also allows you to kind of rotate keys. So if you want to build a secure system for identities, you most likely want to be able to change the keys over time. And so DIDs allows for this. So in Ceramic, we support a few different types of DIDs. In theory, we could support any DID. But we support key DID, which is just kind of like a public key or a public-private key pair. And this is kind of the most basic DID that exists. We also support something called 3ID, which is a kind of scalable decentralized identity with key rotation support. And 3ID is actually in itself a stream in Ceramic. And finally, and maybe most interestingly, we have support for something called NFT DID. And so NFT DID allows any NFT to be used as an identity. So this means all NFTs on all blockchains, currently mostly like Ethereum-based blockchains, can be used as an identity that controls an author's data in the Ceramic network. All right, so once we have this kind of primitive of these sovereign data objects, let's explore how we can actually build user-centric applications with these data streams. So we have created something called IDX, which is a way to store data that's associated with the user, but still have kind of developer control over what the data looks like and how the data kind of can be changed. So in this example, users have their own index of data, and this index is essentially a key value store, where the key is a definition ID and the value is a record. So the definition ID describes what data can be found in the record. And so both the definition ID and the record ID are actually stream IDs. They're actually independent streams in Ceramic. And the index itself is also a stream in Ceramic. And so a developer that wants to build an app can create a definition, and there's a stream that basically contains some information like a name here in this example, a basic profile, a description, and then it contains a schema. And this is another stream that contains just a JSON schema. A JSON schema kind of can describe what is allowed in a JSON object. So in IDX right now, you mainly store kind of JSON objects as streams. And so when a user one here comes to the application, and the application basically asks like, hey, do you have any data for this definition ID? And if not, a new record is created in their index. And this is created by creating a ceramic stream for this record, and then the stream enforces that this schema, that the stream kind of has to conform to the schema. So here, this basic profile schema has a name, and there's an emoji, and there's a description, and that's it. And now we actually have a semantic descriptor. The definition semantically describes the record. And so for other applications, there are different definition IDs that have different structures for data, and the user still can kind of have an overview of all the data that's stored in their index, all the data that they have generated themselves. And so now when user 2 comes to the application, they get the same definition ID because it's the same kind of structure of the data, but they generate their own record that contains their own information, but still conforms to the same JSON schema. So the cool thing here is now when a new developer comes and wants to create an application, you see that, okay, this basic profile is super useful. I don't want to recreate profiles. And there's already a bunch of users that have this data. So I'm gonna just use this basic profile definition in my app. And now we actually start sharing user data amongst applications while users retain control over their data. And so this is really powerful. We kind of start getting like composability of user data in the system. All right, so I'm gonna kind of quickly give a demo of like the API of like how you use IDX. And so we have this ceramic playground. You can find it on our GitHub. I think you can also go to like playground.ceramic.dev. But here I have a console and I'm authenticated to my MetaMask. I'm not going to go through the authentication step right now, but here we can essentially load this basic profile. So I'm going to just do this, await idx.get, and then we're going to call a profile. And actually, first we're gonna get our DAD. So in this console here, in this playground, we actually have a bunch of objects exposed on the window. Here is the DAD of my account. So now I can do this again. Wait, idx.get basic profile. And now I'm going to paste this DID. And so now it basically loads this data from my my index. And here it contains a bunch of information. So this is cool, but like in many cases, you're not going to have kind of this DID, or you might not know it yet of the user. You might only know their Ethereum address. So we can actually do something. So this is assuming your application is using an authentication system with Ceramic called DID Connect. So I'm actually using.
Joel, just to interject, could you? A lot of people are asking for you to zoom in a little. If you could do that, so that they can see it on the. So
yeah.
Them on the screen.
Is that better?
It should be. Is it better? Is it better, guys? On the chat, let us know in the chat. You could zoom in just a little bit more as well.
A little more, right? That should be sufficient.
So that they can see the text. Yeah, that should be good. Yes, looks good. All right, perfect. I'll leave it to it.
Cool. Yeah, just to reiterate here, this DAD object is exposed in the window from this application, and we just get the identifier because I was already authenticated here. And then this IDX object is also exposed on the window, and then we just call IDX.get in that basic profile, and then my identifier. And now, if I don't know my identifier, I can just pass my Ethereum address, and I need to also tell that I'm on Ethereum mainnet. So this is using a type 10 identifier, which essentially appends this descriptor for Ethereum-based chains, and one is the chain ID of Ethereum mainnet. Now, if I do this, I should get the same profile. All right, and so it looks all right. So that's how you can kind of get data, and we can do the same thing if we do idx.set with, let's see, profile. I can update the data. But I just wanted to show as well how you can create a stream in Ceramic. It's kind of going one step lower to just create this data stream. So, and so we have this data stream called file document. And create, let's see if I remember the API here. Oh, this is not correct. Next one. So here. Right, so here I type file document, which is a data stream in Ceramic. I create it, and I pass the Ceramic instance, which is also exposed on the window, and then hello world. And now the stream here that I got, I can get the content from it. And I can also look at the metadata of it, and I can see that it has a controller array, and this controller is the DAD that I'm currently authenticated with. And now I can also like simply update this stream. I'm going to wait this. And now again, if I do content, obviously we'll have an updated here. But we can also do S1 if we want to see the commits. We can see that now there are actually 2 commits here. Let's do this. So now we have actually, we can look at the different commits available, or like that makes up this event log. All right, I think that's it. That's just kind of like a short thing that gives you an idea of like how you can use IDX to store data. And so these definitions can, of course, be created by developers to kind of define their own, how their own data is structured. Let me see if we can stop this video sharing.
Yep. So that was a great session, Joel. It was very informative. Like I also learned a lot from it. There are some questions from audience. Someone was asking how sovereign data is different from dynamic programmable NFTs.
So I mean, it's I don't know exactly what they're referring to dynamic programmable NFTs. In a sense, you could use Ceramic to dynamically program NFTs, I guess, because a stream in Ceramic can be controlled by an NFT, and so where the current holder of an NFT is kind of like the one that is allowed to like update that data stream.
Okay, I think they got their answer. But next question was, tell us little about self-sovereign identity and digital credentials.
Oh yeah, so I guess so. When we started 3box, we were actually part of a different project called Uport, and so Uport was one of the early projects in kind of decentralized identity. And so we were working with this kind of decentralized identity foundation to create this DAD standard. And there's also a bunch of work around creating verifiable credentials as a way to issue or create a signed verification or a claim by some authority that some property is true, right? So the kind of traditional use cases is that someone issues you like a digital passport or digital driver's license or whatever. But of course, like this has a wider range of use cases. And so the verifiable credentials spec kind of works very well with DADs. But the reason we created 3box was actually we saw kind of digital and self-sovereign identities being something that's like much larger than just like, you know, verifiable credentials that you get from your governmental institutions. Because if you think about what your kind of real world identity is, like it's not really about kind of the credentials you get from institutions. It's more about kind of the relationships you have with other people and the relationships you have with the world. And so we kind of wanted to recreate that in the digital environment where as you interact with applications, with users and organizations online, you generate a bunch of data. And based on that data, that's really what makes up your digital identity. And sure, like verifiable credentials and stuff like that are part of that, but it's also much broader.
Okay. Yeah. That was a great answer. Next question was, I think they have background with Solana, so they want to compare IPLD logs to associative account in each Solana programs. Do you know anything about Solana to relate it to the IPLD logs?
Can you repeat the middle part of the question?
Yeah, sure. Is IPLD logs are similar to what we have uh, an associative account with each Solana program?
Okay. Yeah, I'm not super familiar with Solana, but I assume that like in Solana, it's more kind of like of a blockchain architecture where you have the objects or like contracts in Solana like need to have this kind of synchrony assumption, the same thing you have in Ethereum, where the contracts can send messages and receive messages back synchronously without having to like wait for things. And so in that sense, it's more similar to Ethereum than having like an event log for each object, which we do in Ceramic.
Okay. We have one time for one question. What type of algorithm is used for conflict resolution in streams?
Yeah. So right now, it's a very simple algorithm that basically, if there's a conflict, if there's two branches of history in an event log, we use the anchors that go into the blockchain to determine like the time. And if there's a conflict, we'll pick the event that happened earliest. So if there's someone who makes an update later, that will be disregarded. And so the reason we do that is if you make an update that changes which key is like has access to this stream, can actually write to the stream. We don't want the older key to be able to make an update later. That basically is like takes control of the stream again, and that's why we need to pick the earliest one.
Okay, and one last question: does all this transaction in IPLD logs cost gas fee?
So currently in Ceramic, there is no concept of gas fees. Right now, you either run your own Ceramic node to pin the data streams which you're interested in, or you trust some third party to run a node, right? And so there's no like explicit cost, but there's implicit cost in the running of the node. In the future, we're going to add an incentive layer to Ceramic where you can pay validators to keep track of the logs for you, and then that would incur some kind of gas cost. But it would work the UX would be much easier because since you have this kind of event log structures, you can make better assumptions about kind of the how gas is consumed.
Okay. I think these are like all the questions. That was a great session. Where can people learn about Ceramic more?
Cool. Yeah, you can go to. Actually, I was going to show this in the slide, but I guess I forgot. Let me see if I can actually share it. Yeah, you can go to ceramic.network, or you can go to idx.xyz. We have our documentation at developers.ceramic.network. If you want to join our Discord, you can go to chat.ceramic.network.
Yeah, I think let's see. Yep, I think that's it for the session. Thanks for joining us. This was a great session. I hope developers learned a lot from this, and they will come to Ceramic to build some awesome apps.
Yeah, thanks for having me.
Yep, thanks.
Thank you so much, Joel. Thank you so much, Nigel. Thank you, Joel, for doing this session. It was really great and informative. Yeah, we'll stop this right now, and our next session begins at 3:30. We're sitting down chatting with Christina Cornet. She's the editor-in-chief of Cointelegraph, and we're taking questions, and we're discussing the role that communication plays in the crypto industry. So we'll see you then. See you in 15 minutes. Thank you.